linear recursion, or linear growth and decay, is where we go up and down by a common difference. And that difference was either plus something or take something. In geometric growth and decay, we don't go up and down by a common difference, we go up and down by a common ratio. So we multiply to get from one to the next. Now, graphically, in a simple example, that looks like this. If we have TO equals 1, meaning TO equals 1, we're starting there, when n equals 1. And if we have this axis here as Tn, then we get from 1 to the next by multiplying by 2. So by 2, by 2, by 2, and by 2, and the next one will be off. You can see here that each time we multiply by 2, we're doubling. It produces a curve. Geometric decay should be modelled using a curve. Geometric growth, a curve. Now note, this here, this 2, is called the common ratio. So the common ratio, it's quite an interesting concept. And what we do is how we get from one to the next. So our sequence looked like this. It's a pretty easy one. Now to find the common ratio, that was meant to be an R, we do Tn plus 1 divided by Tn. So that means we take one term and divide it by the previous one. For example, we could do 16 on 8, or 8 on 4, or 4 on 2. Either way, they all come up with the same ratio. One term divided by the previous one is always going to be 2. Alright. Now, what about geometric decay? Geometric decay is still done using multiply, but we're multiplying by something less than 1. Geometric decay, I should point out, is when r is less than 1. Alright. Now, if r is less than 1, in this case a third, we have TO is 273, just about there. And if we go 1 across and drop that by a third, what will happen is we'll go down to 81. The third of 273 is 81, which will be there. Then drop that by a third, we go down to 9. Drop that by a third, we go down to 3. Drop that by a third, we go down to 1. Drop that by a third, we go down to a third. And while I can't show you very clearly with these very big circles, what should be happening is we are curving down here. And while we're getting very, very small, we're never going to reach 0. Alright. Once again, so our sequence looks like this. 243, 81, 9. Oh, I jumped one there, didn't I? Divided by 9. 81, 27, 9, 3, 1. Apologies, but you get the idea. We still curve down. 27 is a bit lower than that. And to find the common ratio here, we still do Tn plus 1 over Tn. So that could be taking, say, 9 over 27. 1 divided by the one before. Or 81 over 243. Or 1 over 3. Either way, the common ratio is 1 over 3. Take 1 divided by the previous gets us the common ratio. In linear, you take 1, subtract the previous, gets us the common difference. Alright, now, while doing this, we often want to model percentage growth or decay. This should be a recap, but in general, to increase something or decrease something, we use these two equations here. So, to increase 100 by 15%, decrease 100 by 15%, we multiply it by 0.85, and that 0.85 has come from 1 take 15 on 100. That is equal to 0.85. Alright, now, this is applied very, very commonly in compound interest, where interest is earned on the amount of money invested or borrowed, including earned on the previous interest. So, for example, an investment of 15,000 earns 3% interest per year compound interest. Write a recurrence relation to model this scenario. Well, we start with 15,000. Not bad. Then what happens after each year? Well, after each year, this 15,000 earns, so it increases by 3%. So to get to Vn plus 1, what we're doing is we're taking Vn and increasing it by 3%. Where that 1.03 has come from 1 plus 3 over 100. That multiplier multiplies to effectively increase it by 3%. So V1's there. If we look at V0's there, if we look at V1, we do 15,000 times 1.03. Which is going to be 15,450. Then, to get to the next one, we don't take 15,000 multiplied by 1.03, we take the term before and multiply that by 1.03. Which is 15,913.5. Now note, this here increased by $450 on the previous year. That was the 3% increase. However, the next year it increased by more than that amount. Another $450 would have got us to 900, but we're at 913. This is the power of compound interest. Each year it grows by a larger amount. Right, how much would this be worth after 6 years? Well, the best way to do this is probably on our calculator. We can go here. We can look at, well, we start with 15,000. And then we want to do the previous year increased by 3%. Equals, the previous year is B1, and we want to increase it by 3%. Ooh. Okay, that's a silly error. I actually entered it in B2, so we're just going to go B2. Remember the equal sign. Alright, apologies. Different screen now. Calculator was playing up. Equals C1, where my 1500 is, 15,000 is now, and then we want to increase it by 3%, 1.03. Enter. Alright, that's what it'll be at the end of the first year. Now we drag it down. Okay, if we went a bit far, that doesn't actually matter. End of the first year, end of the second year, which is what we calculated by hand. End of the third year, end of the fourth year, end of the fifth year, end of the sixth year. Now note, sixth year is actually on the 7th line, so be very careful there with which year we're choosing. It will catch people out. So our value was $17,910.70. Lovely. Now, this can also be used to model depreciation, so decreasing by a percentage each time. So, take my car for example. My car has an initial value of approximately $30,000. And unfortunately, being a car, it will lose its value relatively quickly. I will lose, let's say, 20% a year. It gets used a lot. So what we want to do is say, well, to get to the end of the next year's value, it will be worth the previous year, then decrease by 20%. Now, decreasing by 20% is the same as multiplying by 0.8. That's come from one take 20 on 100. That decreases by 20%. And this should be stuff that you've pretty comfortable with from using before. So then if we take 30,000, multiply it by 0.8, at the end of next year, my car will be worth 24,000. That's depressing. I've lost 6 grand in a year. However, then for the next year, when we take 24,000, multiply it by 0.8, we're going to get 19,200. Depressing, I've lost money, but I haven't lost another 6,000. I've lost another, well, what's that, 5,800. Not ideal, 4,800, but not so bad. Not as bad as the first one. V3, we take the previous value, multiply by 0.8 again, And once again, now we're down to 15,360. So in 3 years, my car almost halves its value. Rather depressing, alright? But this is how we use recurrence to model percentage increases or percentage decreases in consecutive years. Please leave gaps within there because we'll go back and do the rule in a second. Alright, thank you very much. By a second, I mean the next video.